Integration is terrific for finding areas, but it relies us on knowing how to integrate the function. And there are some functions we just don't know how to integrate. Yeah. So approximations are going to be the best we can do. Earlier we estimated with a rectangle, and the overestimate was huge. But we can cut that down really easily by, instead of making it a rectangle, we make it a trapezium. And so there's that whole triangle now that's missing from the overestimate. So that's a quick way of getting a better estimate. We use a trapezium instead of a rectangle. So in that case, our area would be, well, half the perpendicular height, which in this case would be b minus a, and then the sum of the parallel sides, so whatever function a is plus whatever function b is. But just like we saw with the rectangles, the more trapeziums that we have, the better the estimate's going to be. So let's put another point in there, we'll call it C, and you can see straight away that the overestimate is a lot less. So our area would be, again, each of those trapeziums, perpendicular height divided by 2, but we've placed C in the middle of A and B. So the difference between C and A would be the difference between B and C, the exact amount. So we could actually factorise that, because C, as I say, C minus A on 2 would be the same as B minus C on 2. And we get function A plus 2 function C plus function B. All right, let's make it 3 trapeziums. Okay. So we'd have 3 trapeziums, the formula 4, but again, C minus A would be the same as D minus C, would be the same as B minus D, so I could factorise that out, and a pattern starts emerging. We always get whatever that factorised height divided by 2 is out. And inside, function A and function B is always there, but twice the ones in the middle. And the reason it's twice the ones in the middle is because they're involved in 2 of the trapeziums, so it comes up twice. So the way I remember the formula, there's the exact value, of course. My approximation, the perpendicular height on 2, whatever the height of the trapezium is. Y naught and yn, I'd call the 2 end ones, and then it's just 2 times the others. So whatever the y value is for the others. Now, that perpendicular height will always end up being b minus a divided by however many trapeziums that we're going to have. You'll always end up with one more function value than you do the number of trapeziums. Okay, because you'll notice there's 3 trapeziums, 4 function values. So you'll always have one more. And sometimes you'll see them called trapeziums, sometimes they might call them strips, sometimes they call them sub-intervals. They have all sorts of weird names that they use, but they all mean the same thing. So let's actually use it to, find the area under this particular curve. Now I've picked this one on purpose, so at this stage we don't know how to integrate that. But we should be able to find the exact value, because if you recognise the function there, it's our semicircle. So we've got a formula that would allow us to find it exactly. So that way we can compare how good our approximation is going to be. So we're going to use 4 intervals. So first of all, let's work out how high each of the trapeziums is going to be. So 2 minus 0. Now they've said 4 intervals or 4 trapeziums, so we'll divide by 4. So half. Each of them are going to be a half. And then just draw up a table of values. Naught, half, 1, 1.5 and 2. Work out each of those function values. There's my formula. Y naught, yn, 2y the others. Just to remind myself, on my table of values I say, okay, it's going to be 1 times the end ones and 2 times all the ones in the middle. Just a way of remembering, okay, these ones I'm multiplying by 1, these ones I'm multiplying by 2. So when we sub in, 0.5 on 2, as I say, the end ones are just times 1, but then 2 times all the ones in the middle, and we get 2.996. Now, I said we could work out this exactly because we know it's a semicircle. In fact, it's a quarter of a circle if you think about it, because we're only going from 0 to 2. So the exact value actually turns out to be pi. A quarter of pi r squared, the radius in this case being 2, so a quarter of 4 pi. So how far off are we? Well, exact value is pi, so the 3 decimal places, that's 3.142. So we got a 4.6% error. Of course, we could get better by using more trapeziums. Well, okay. Then this fella Simpson came up with an idea that why are we estimating areas under a curve with a straight line? I mean, it's never going to be exact until we get to infinity. So he came up with the idea of why don't we estimate the area under the curve with a curve and use parabolas. And this is what he ended up coming up with. So there's the exact one. That's very similar to the trapezoidal rule, but a couple of key differences. The perpendicular height is no longer divided by 2, it's divided by 3. Still 1 times the end ones, but now it alternates. The odd ones I'm going to multiply by 4, and the even ones I'm going to multiply by 2. Now when I say odd and even, I don't mean the number. Remember I called the first one y0? So the next one would be y1. That's what I'm calling an odd one. The next one will be y2. That's what I'm calling an even one, and so on. And basically it alternates. B minus a on n is still the same there. So let's do the exact same question. There's the table of values that we had. But now I'm going to use Simpsons Rule. So 1 times the end ones, and then it alternates 4 to 4. Simpsons Rule works best when you have that symmetry. So had I had 1 less function value there, and I would have gone 1, 4, 2, 1, probably wouldn't be as good an estimate as when I've got symmetry. So if we sub those values in, and we end up with 3.084, which is a heck of a lot better. Remember the exact value is pi. In fact, the percentage error there is just 1.8%. So a lot closer. So what we're actually doing there is estimating with parabolas. So we're estimating a curve with a curve. Now, there's another way of setting out the working, which is quite neat. Let's go back to our trapezoidal one. Remember the pattern was 1, 2, 2, 2, 1. There's the area. Now look at it very closely. You'll notice on the top of the fraction is still that 1 times the end ones, 2 times the middle. The bottom of the fraction mirrors the 1, 2, 2, 2, 1. And then we multiply it by the overall width of our slice. So going from B minus A. And that in fact does turn out to be 2.996, of course, because that is the answer. So that's an alternative way of setting it out. You still, as I say, have to do the end ones, 2 times the middle ones on top. On the bottom, you just mirror the pattern, 1, 2, 2, 2, 1, and then multiply it by whatever B minus A is. Okay? And it works for Simpsons Rule as well. So there's our table of values. So this one, on the top, I'd go 1 times the end ones, 4 times and 2 times the middle one, and on the bottom, mirror the 1, 4, 2, 4, 1, multiply it by B minus A. And it comes up with, obviously, the right answer. So 11I and J, which I assume one's on trapezoidal and one's on Simpsons, I would assume, is what it is there.